In this project, we're tackling pathfinding, A-star optimization, and just getting a crapload of units onto the screen and moving around all at once. I ran across this cool video from Brackeys, who stress tested the limits of Unity's pathfinding system and was able to get around 10,000 agents running simultaneously, and I wondered, how many could I get going in a single simulation in JavaScript? Now, I have a few things working against me. Unity is heavily optimized, and I'm working in JavaScript. But I have a whole bunch of ideas on what to do, and I'm granting myself permission to bend the rules a bit so that if things aren't doing things strictly correctly, no big deal. In general, pathfinding is pretty neat because it's pretty much at the heart of any game AI. You almost certainly need a strong A-star implementation. I've never done much game AI work before, so this is all pretty new to me. It was really a chance to fiddle around with parts of the code I've never done anything professionally with. A while back, I already did a basic A-star implementation, which walks you through the basics of the algorithm, how and why it works, and how to implement it. Today, we're taking that a bit further. So let's mess around a bit, concentrate on A-star optimization, and see just how many AI units I can have running around on a reasonably complex map. Sound good? Like always, code's available. Check the description below, fork it, do whatever. What we're going to go over today is, I'll show you how I got from one little guy wandering around the map to many little guys wandering around the map. So let's start. First, we need a map. Now, I can just model it in Blender, but then I got to do that every single time I want to try out a bigger or smaller maze. So that's no good. Luckily, we happen to have one, or at least a way to get one, since I already wrote a maze generator using recursive backtracking a little while ago. The only problem is that it's 2D. No worries. Let's just import the code and we'll screw around a bit and turn it into a 3D mesh. Here's where that magic happens. On the left, you have the original 2D map drawing code. What this did was that it traversed the graph, looking at each node's neighbors and whether or not there were edges between the nodes, and then drawing a line to represent a wall. In the 3D version, you traverse the graph looking at each node's neighbors and whether or not there are any edges between the nodes, and then you create a rectangle. Afterwards, when this is all done, we merge them into one massive static mesh and add some ground underneath. Now, we don't want strictly a maze, since that's typically one entrance, one exit type of deal. So afterwards, we'll go over the maze and make a whole bunch of openings everywhere, making it easier to find multiple paths from the top to the bottom. Is this the most efficient solution ever conceived? Not really, but it works, and it's fine, so let's just move on. So we have a map. Next, we have to make a unit move, and luckily again, I implemented boids a while back. Boids is just a term for a loose collection of steering behaviors that you can apply to an individual agent, or boid. I'm going to repurpose that code, but strip out all but one of the behaviors, the seek behavior. We'll keep that one, and we'll add a path-following behavior, which is given a list of nodes representing the path, and the boid will seek from one node to the next following that path. And that'll give us a working path-following AI guy. See, watch him walk along. And no matter how complex the path, this little guy will find a path through and then navigate the path with ease. Alright, so we're all set up. We have some procedurally generated mazes. We have an AI agent navigating the maze. Now let's make this fast. First, we need to do some A-star optimization work to improve performance. I already covered a basic A-star implementation, going over the core of the algorithm and its implementation, how and why it works, and how the heuristic guides the expansion of nodes. That basic implementation works, but there's some room for improvement. The first thing I did was create a separation between a running instance of an A-star search and a pending one. So we create this A-star management class that creates proxy clients. The job of the A-star client is to serve as a thin client between the manager and AI agents that need a search to be performed. What they do is wait for the manager to pass them a running instance of A-star, and clients can check if their search is pending, active, or finished, and get the build path. All this serves to gate the number of running instances of A-star, since if we have, say, 10,000 AI agents running through the scene, we don't want to try and run 10,000 instances of A-star all at once. Next, I tweak the heuristic. Normally, when you're shown how to do A-star, it's with a distance to goal function, or what's called an admissible heuristic. I'm changing this over to use Manhattan distance, since this is a grid and Manhattan distance is more correct, and also cheaper to perform. I've also made a very slight change here and added a multiplier on the heuristic. This means that the heuristic we're using is no longer admissible, but this has the effect of making A* run in fewer steps. The trade-off is that the paths it chooses are no longer guaranteed to be optimal, but that's fine for our purpose. Now that's all enabled, looks like I can bump this up to around 4,000 units or so before the frame rate begins to drop. Here there are 4,000 separate units all doing pathfinding through a fairly massive scene, and we're comfortably running at 30 FPS. There are still more A* optimization ideas and tricks I could try out, but at this point we're render bound due to the enormous number of meshes, so let's fix that. What we're going to do now is move our meshes over to use instancing, which is just a way of drawing large batches of the same object quickly. What it does is reduces the number of draw calls and thus material changes and that stuff that the API and driver need to handle, thus reducing the overall CPU usage. You can see the second we switch to instancing, we can bump up our agent count. And it looks like we can now support around 15,000 AI agents or so wandering around through the maze at a comfortable 30 FPS. Bumping it up much beyond that tanks the frame rate, so we're going to have to try and fix other things now. Taking a quick profile using DevTools, a few easy things pop out. We're spending a lot of time updating the matrix, and we're also incurring some garbage collections from JavaScript, most likely due to allocations. Let's go and fix those. Managing the world matrix ourselves instead of having Three.js do it, and pre-allocating some vectors and matrices to work with, and suddenly our frame rate shoots up even higher. Here's 60,000, and still at a comfortable 30 FPS, which is pretty good. They're all navigating the mesh independently and doing a full A* search for their path, so there's no pre-computation of paths or anything of that sort. No funny stuff here. And that's where we'll end this. This was really just for fun and kind of screwing around. Maybe you can use some of the ideas in your own projects in the future, who knows. I'm pretty sure I can get into the hundreds of thousands, but that'll require some more work and planning. Move things into other threads or even push work onto the GPU. I've got some ideas, and if I decide to act on them, I'll make a video about it. Thanks for watching, everyone. I hope you learned something. Remember to hit like and subscribe, and also comment and let me know what you thought. Until next time, cheers, everyone.